Okay, so welcome. We've been talking in class about one of the first model-free, if you will, methods that we are going to be implementing this semester, and it's in a way one of the most simplistic ones, and that's K nearest neighbor. And we discussed a lot of things, specifically on Wednesday, regarding complexity parameters and tests and training. And although we didn't formalize every aspect of it, a lot of those things you're going to see again in this lab. So what I've done here is I have put together a code here, which I'm going to call KNN 2014. And in this code, I'm going to, I always put a heading here just so that when I go back to things I can understand. First of all, it was created a couple of years ago, the code I'm working from, but I added some modifications this year as well. So I just like to keep a record of those kind of things. And the same is true with my research. I always date my codes because we always have different versions floating around and so forth. So the first thing I'm going to do is I'm going to just clear the workspace, okay? And I'm going to set my directory. And one quick way to do that is in R, because the paths are always different. So I'm actually on a Mac, and if you're in Windows, I believe you can do the same thing. I typically go to the folder that I want to work from, which, let me see here. I think we'll actually, not course materials, if we look at Complabs, this is going to be the code, or this is the folder that I want to have as the directory. So I just click and drag it. And if I were to hit enter here, I would get an error because there's no command here. But I can use this path and embed it into a set WD command. And now what I've done here is I've just flipped the directory. So now I'm within that directory. And what I need to do is I need to once I've set the path, I need to install the libraries that I want to use. And the one that we're going to use today is ggplot2. And this is a CRAN package, so if you need to install it, you can do install.packages, ggplot2. It's a great package. It was developed by some pretty heavy hitters in the stats field, actually. And what's really nice about it is R's graphics are kind of very fundamental. They're very difficult to work with. If you do a help plot and a help PAR, you can see just what I'm talking about. One of the most clear things is, first of all, aesthetically, they're not very pleasing. But the other thing is they don't have handle graphics like you would see in MATLAB, and there are many other problems with them. So ggplot2, if you there's a book about ggplot2. It's a very simple, it's kind of like a pamphlet almost. It's a great read. If you really start to need to do some more sophisticated plotting in R, I suggest it. We're not going to use ggplot2 all the time. Often we'll just use the default graphics in R, but what I want to do is just show this to you today because we're doing something kind of unique in terms of visualizing the K nearest neighbors. And we will, in fact, load and visualize the data. So when we read in the data, sometimes we have data that we'll just take from a particular package. Sometimes we have a data set that's in a text file. We have to read it in. And so I'm going to call the data here. I'm going to say read.dlim, which is a special case of read.table. It's kind of, if you ever have a problem with reading in data that's really big, read.dlim will not choke and read.table will, so I always default to this one. Clipped data, .txt, and this data set is really simple, and if I show you, so here I am, let's see here we are. Course materials. Oh, I always go there. Complabs. The data set is actually here, and this is also, if you haven't done so, download it from UB-Learns and put it in the directory that you're working from. There's only two variables here, x1 and x2, and then there's a third column, which is a response variable. and it's two classes. This tells me that the data is tab delimited and that there is actually going to be no header. So that's how we read in data, and you can always use this command to recycle it, changing. You could have comma delimited, you can have other things. If you do a help read delim, you'll see all the choices that are there. So what I'm going to do here is I'm going to call an object train, and I'm going to use a function called data frame. Now R has many different objects. You can have a data frame, you can have a matrix, you can have a list structure, you could have a, my mind is blanking, an array. There's many different things. So here we have a data frame, and we have the first column, I'm going to say, is from the data that we read in, and it's the first column of that. So this says take everything, every row, by leaving that blank, it says take every row in the first column. And then here we have x2, we're going to call x2 is data, and y is data 3. Okay? And I'm just going to read that in here. Okay, so that actually made that into a data frame. And so sometimes when I want to understand the data, I will say things like dim train, which will tell me the dimensions, and I use head all the time, which gives me the first bunch of rows. Okay, so this just gives me, it's 200 by 3, and if I were to type in train, it would give me all 200, but that's hard to kind of see. I just want to kind of get a feel for the structure. I have an x1 and an x2, and I also have a y, a response, which has two values, 0 and 1, which the ones are at the bottom, the kind of like the second 100 there. So what we can do is we can actually plot this data. So this is a very simple example. We're not usually so fortunate as to only have two predictors, but since we're going to start out slow, and we kind of, not slow, but we want to visualize. Let's start just by visualizing, and really anything more than two becomes kind of cumbersome with k-nearest neighbors. So we're literally going to kind of set up a problem where we recapture some of the plots that we saw in class and in your book. And I'll show you how we're going to do that. The first thing we're going to do, though, is we're going to plot this data according to class. That means I want to code one class one color and the other class the other color. And so we're going to use ggplot2, and we're going to say ggplot train. And we have AES, which shows the variables that we're going to use. And so if you look into ggplot, I'm going to kind of do this, and then we'll kind of talk about the different pieces of this command. So here we have the geom plot AES by color as factor y. Okay? This tells it it's a factor and not a numeric string. Important. Theme, and for that we put in legend.position is equal to none. Okay, and I think that's all we need. So this is actually how you do plotting in ggplot. Now, how you do plotting in R is very different. So if you do help plot, it's very simple. And you can actually do a plot similar to this using R. But what we're doing, and when you use ggplot, we're plotting the training data. X1 and X2 are the variables we're using. And we're going to color them according to the factor, and we're not going to put a legend in there. So there's some different components, and if you get the book for ggplot2, which you don't need to because there's just loads and loads of resources for how to use this program. It's a little bit cumbersome at first, but it starts to pay off in dividends if you get to know it. It works like a layer. This is the basic thing. And then there's many different options that you can add to it. The geom plot is one layer and the theme is another layer. And there are other things we can add to this, and we will. And so if you run this, geom plot. sorry, this should be geome point. Okay, okay. Now let's see if it complains. Okay, so we have a G. And what we can do with this G is we can, the other thing is, even though this is a plotting command, it's not going to plot it automatically. So what we can do if we want to is we can say x11, or you could also do quartz. Quartz used to work only for Macs, and I couldn't use X11 for a long time, but now with this new version of R I can use X11. So if you're on a Mac and you have trouble, those are the two things you can kind of go between. So I'll just kind of put a comma in here. I know that in Windows you can always use X11, there's no issue there. But this X11 or the quartz, whichever you decide to use, actually calls up a window, and what we can do is plot G. Okay. Okay, so this is kind of looks nicer than the typical graphics you would see in R. It's got that nice beige background and a nice looking grid, good size points, and I like it. So what we have here are two classes that are fairly well separated. I can see, if I had to guess, I would say it's some bimodal distribution here for sure. It doesn't look like a mixture of 10 different pieces. And we might have some success here. So the other thing I'm going to show you is how to save a picture. And we can use ggSave, which is part of the ggplot package. And you have to tell it a file name. So when I use these commands, you might want to pause the video and just do ggSave and just take a look at these things. Okay? Get used to the way the help files are kind of the flow of the help files, and some packages they're more extensive than others, and some packages they're too much, some packages they're outdated, so but they're useful, and I won't take time to go through each one. So I'm going to call this orig.png. I like to use PNG files when I save images in R. They're kind of smaller in terms of size, and they have good resolution. If you are a LaTeX user, you might want to use an EPS file instead. Sometimes there's trouble with compiling PNGs in LaTeX. Now, these are some parameters that I might set. Height and width of the plot. This is the actual thing that I want to plot in the file name. So I'm going to run it from here. Okay, and nothing happens, but if you go into your directory, oh wait, this just doesn't want to stay open. You can see that it did save it, and here it is. It looks really nice. Okay, so I've closed that. Okay, so the next thing we're going to do, so one thing that we talked about that was critically important was this idea of training and testing data. You're handed a data set, and you have to do something with it. You really want to try to kind of assess how well it's going to do in the general population. So this division of test and training, although there are more sophisticated ways of doing it, the simple is to take part of it and put it aside. What I did here was I read in a data set and had two measurements, and I decided all of it's going to be training. You wouldn't typically do this, but what we're doing here in this situation, I'm going to actually create a test data set. You might say, well, how would you ever do that? Well, what we're interested in doing here is to have a long-term goal of visualization to start to understand what's happening, okay? For different values of k and in the different regions of the space. It's not our goal at this stage to estimate generalization error, okay? We'll have plenty of time to do that. So in order to do that, what I'm going to do is I'm going to take all of the data that we had as training, And I'm going to create a grid of points that spans the range of that data and use that as test data. And if I do that, I should be able to, by using k-nearest neighbor, use the training points to make calls for each point in that grid. And I can color the regions accordingly, which is essentially what was done in the book. Okay, so we're trying to kind of recapture that. What spaces, if a test point would land in any space, what would it be called? Pink or blue, or 0 or 1? So the first thing we're going to do is we're going to find the min and max of the different variables. So we have an x1 and an x2. And so I have this data called train. And if I look at this, one way I can look at this is I can say train 1. And this is actually, if I look at this data, it gives me all 200 values for x1. Okay? So we kind of see what that looks like. Another way I can access the different columns is to say train x1, where I have a $sign, and this is going to actually give me the variable x1. And it's the same exact thing. If you look and check the numbers, it's the same exact output, just different ways of calling the same thing. Why would you prefer to use one over the other? Well, this is ideal if you have 10 variables at most, or 20, where you can actually count and figure out what column it's in. You have, less chance for mistakes. If you have 40,000 variables, how are you going to identify x1 in a stack of 40,000? Well, if it's sequential, it's easy, but what if they're non-sequential? So I typically try to use this notation. There's this calling mechanism where you use a $sign and then access the variable that way. So why is that important? Well, what I simply want to do is I want to find the min of that, okay, which is minus 2.52. So if I were to look through here for the min, that's what it would be. That's the command for min. And likewise, I want to find the min of x2, and we will do that the same exact way. Okay, and the max of x1, max train x1, likewise, and the max of x2, which is the max of train x2, and I can see here I have a typo. Okay, so let's just run this. And when you run these, the output doesn't come. You have to actually call it again to see what the values are. And let's just see, are they in the same basic range? And we will see that they are. Okay, so the ranges are a little bit different, but I think it's pretty close. So what are we doing? Remember, we're creating a test set, and this is going to be a grid of values. Let me put it down here. A grid of values spanning the ranges of x1 and x2. So that's pretty neat. We get to generate a grid together on one of the first labs. It's not trivial to generate the grid. You have to kind of think about it. So let's start by figuring out what the x1 range is. We found the min of x1 and the max of x1. So I'm going to create a variable called x1.range, and I'm going to use a great command or a function that I use all the time called seek. This will give us a sequence of points from the min of x1 to the max of x1, and it's going to give us, it has a command called length.out is equal to 100. So it gives 100 points between the min and the max. Okay? And so if I look at x1 dot range, that's what we have. Okay? So it's just interpolating between that space. And there's a lot of flexibility with this seek command. I suggest you do a help seek to see exactly what we can do there. Very, very convenient. So you might say, well, if I were really being particular about this, I would probably start from the min x1 plus delta, or sorry, minus delta, to the max x1 plus delta, because you don't really want to end the range on a data point. But I think, for what we're trying to do here, I don't want to get that particular. That's the devil is in the details. So here we're going to do the same thing for this, and min x2 to max x2, and we have length dot out is equal to 100. Okay, so that will essentially give the range for x2 at this point. And now we're ready to create a test set. Okay, so these are the ranges. And then we have create the test set. Okay, I always comment things. I try to anyways. And so for that, what we're going to do is we're going to call it test. And we're going to use the data frame object again to create a data frame. And that data frame is going to be an x1 variable in the first column. And I'm going to use another great command called rep. So do help rep. It's my favorite. It's one of my favorite commands. Replicates the values. Very simple command, but extremely useful. You can replicate 0 10 times. You can replicate 100 10 times, 110 10 times. You can also replicate letters or character strings. ABC 10 times. Okay, so it's very flexible. It's a fantastic command. So we're going to use it here. We're going to replicate the x1 range that we just found 100 times. Okay, so we're just going to copy that range over and over and over. And, whoops, you know what? I forgot the rep command. Okay, so that's x1 range. We're going to do that 100 times. And then we're going to have for x2, we're going to replicate x2 range. I'm going to use each is equal to 100. So we have to use the rep command for the second piece a little bit different. So here we replicate the x1 range 100 times, but this one is going to replicate the x2 range also 100 times, but it's going to do so in a different way. So let's just look to see what this looks like. Okay. So they both have, you know what, let's run this and then we'll look at the test set and I'll show you what that does. Oops. X2, oh, I forgot to run this piece first. I'm going to just run it from here. Okay, so now I do head test, and you'll see what I mean. Okay, so this runs over the range of x1, okay, and then for x2, it simply stacks them up. So if you think about, I guess you could do it a few different ways. This is the way that I would do a grid. So here, this is x1 range, there's 100 here, and then there's another 100, always in sequence of the range. For x2, it takes the first value and it replicates it 100 times. Then if you go to entry 101, let's just go down. It might be obvious, but I'm thinking it's not, so let's just go to 105. Okay, so you can kind of see what's going. This is running over the range of x1, all for the first value of x2, and then here, running over the entire range, all for the second value of x2. So you can imagine that's how I'm filling it in. Okay. Now, I want to save this. Okay, so we have the test set, and now what we need to do is create a plot. So I'm going to say G2 is equal to ggplot test. So it's the same exact start as we had before. And we have to add to it a simple piece called gmPoint, which this is another setting you can find in ggplot2, another layer. The size of the points, you can play with that as well. I'm just going to shrink it a little bit because we have a lot of different points. So I'll run this, okay, and now what we'll do is open an X11 window and plot G2. So let's see what that looks like. Okay, and it looks like a grid, exactly what we would have expected. So that's a quick way to generate a sequence of points and a grid from that. Now what we're going to do is we're going to kind of get into the hard stuff. So, not hard, but the actual meat of the code. We have now, what we've done is we've read in this data. This is going to be our training data. We've created a test set, really not with the objective of estimating generalization error at this point, but simply to guide in some visualization. So every point actually in this test set is going to be classified according to the training data. Okay, so if this point is closest to 2 pink dots, it's going to be pink. And from that, we're going to see regions and boundaries as well. So here, we're going to try different values of k. And so this is going to be possibly your first function you're writing. And when I write functions in R, I typically try to keep them as general as possible. And this is going to be a way for us to write our own function, just like ggplot is a function, just like rep is a function. The function that we're going to write, we're going to call it knplot. And the command we use to set it up is function, and we have to specify its input. And the input to this function is going to be very simple. And it's also going to reflect the input you would kind of expect for any classification function. In particular, we need the training set, we need a test set, and we need k. What else do we need, really? That's it. So we'll bracket this off, and everything between these two brackets will be part of the function. So the actual command knn, it's part of the classification package, and so right up top I'm going to put require class. Okay, so we could also put library here. We could load the library. I tend to use require when I use in this context for the functions, but either way will work. And so I'm going to call the output here knn. So you should really look into this function at this point. You should kind of pause the video and see what's involved there. It's pretty simple, but it takes a little bit of understanding of the syntax. So I'm going to use knn. I'm going to use my training data, all of the rows, and I have to tell it what columns I want to use. And so C is a character string of columns, and we have x1 and we have x2, okay? Because remember, the training set has 3 columns. The third one is the response. The second input to knn is the test data set. The third input to knn is the true labels for the training set, which is, if you remember, the third column, or y. And the last thing we need is k. Now I'm not going to specify k because I'm writing this in the most general sense possible. And so when I'm debugging, sometimes I'll say, okay, k is equal to 1, and then go through just one time to see if it works. But I know this works, so I don't really have to do that at this point, unless we come up with a bug, which would be probably from some syntax. just like I can call objects in this way, I can also append objects. So I'm going to create a column in the test set called predict, and it's going to store the KNN objects. Okay? And so why don't we just say that K is equal to 3 for simplicity, and I'll kind of show you what some of this output looks like. Okay, if I type in KNN, what's the output going to look like? It's a bunch of labels. These are the predicted labels for KNN for K is equal to 3. And this is for the test set, right? Because look at how many values there are here, of course. And so now if I do this, if I do head test, you can see I have a new column here what I didn't have before called predict. These are the predicted labels for these values. Okay? The next thing I'm going to do is change factor to numeric. So I'm going to create another appendage to test, and I'm going to call it Z. And here what I'm going to do is this is a numeric vector. So if I were to say test predict, this is a factor, and I know it's a factor because it says it has 2 levels. Now there's a couple ways you can do this. You can say as numeric, we want to convert it to a numeric vector. If we do that, what happens is it starts at 1. It's just the nature of R. It starts at 1. We want a 0-1 response, right? Because we have a 0-1 training response. So you could do something like this. That would be fair game. But I tend to use a more general technique to converting factors to numerics, which you'll have a lot of practice doing this as time goes on. It may seem a little puzzling for right now. But what I'm saying is I want to change factors to numeric. I'm saying I want the first level vector to be 0 and the second to be 1. And I use a command called sapply and test predict as numeric. sapply is a way for us to, if you do help sapply, you'll see there's a whole bunch of applies. There's an L apply, an S apply, a V apply, a replicate, all different kinds of things. This allows us to actually execute the conversion over the entire vector. Okay, so if I were to do this, I get the same exact thing as if I were to do this. So whatever is easier for you to think about. Nonetheless, I'm going to add this piece here. So now if I look at test, it's growing. Okay. The other thing I'm going to need is a title for our plot, and the title is going to be a function of what the input is, really. I'm going to use a command called paste, another one of my favorites, and I'm going to paste K is equal to I'm going to take whatever K is, it's a number, I'm going to put it into a character, and I'm going to separate it using nothing. Okay, so paste is a great command. I could separate it using anything I want. Okay, so if I look at title, K is equal to 3. Okay, I could also, I could have done it like this. I could have said K, and I could have put a separator as being an equals, and if I look at title, it gives the same result. Or I could have said anything fancy in here. You can, it's a completely flexible thing. It literally pastes together a bunch of stuff, and now I have, a title. Now the tricky part, ggplot, and we're going to start, we're going to layer this. So we're going to say data. Okay, I better pause here. Okay, so now we have power. We can say data is equal to test, AES, x1, x2, okay. There we are. Plus geom point AES color. That's going to be equal to the predict column. Okay, so we're going to color them by the predictions that are given for the test values. The size is 0.5. And let's see what else we need. Okay, we're going to create a contour line. Which separates the classes. C is equal to C. Okay, so to create a contour line, this is actually more complicated. It took me a while to figure out how to do this. You can just bear with me here. Black. And the size of the line is 0.1. Okay, so that's another layer. The other thing we have to tell it is a theme legend dot position is equal to none. Okay, we don't want a legend. We have to tell it that. And for the labels, we'll say the title is equal to the title that we gave it. Okay? Now I think that's okay. I always seem to mess up a comma or something like that. And now what we're going to do is literally add the training points in. So we will say G is equal to G plus. And now we're going to use the same kind of stuff we did before. Geom point data is equal to train AES x1 x2 comma color is as factor y. Okay, so we're in the training data. It knows it's the y column, and we can also add. Sorry, I'm seeing commas here. Shape is x. Okay, you don't need all of that stuff, but this is going to take G. It's going to add on top of it the training data. So you could have left it just like we had it before. This is going to make it stand out a little bit here. So what I'm going to do actually is I'm going to save it first. I like to save a lot, especially because some of these plotting devices seem to have a lot of problems with them. So the last thing that we need to do is when we write any function, we need an output. So what's the output going to be? We're going to actually return G. Okay? So what I'm going to do is I'm just going to literally run it from the top, just get a good clean run. Okay, and it ran quickly. There doesn't seem to be an obvious bug, but if there's a bug in this function, we won't know it until we actually run it. Okay, that's kind of the trick. So let's go ahead and apply this to our data for different values of k. And I'm going to make use of that save command to save the graphics, and I'm going to create a string of file names using paste, and I'm going to call it k c 1 through 10. So what does this do? Okay, that just gives a string from 1 to 10. And I'm going to paste to that .png, and I'm going to separate it with nothing. So let's just look at what the file names look like. Okay, those are the files that are going to be saved when I write a for loop. So what we're going to do in this last piece, final piece, is we're going to actually try different values of k and save them into a directory. Okay? And to do this, we're going to use a for loop. So imagine if you want to do something for k is equal to 1, you want to do the same thing for k is equal to 2. The only thing you're changing is k. So it's really easy to think about this. Might be your first for loop. For I is in 1 to 10, p is equal to KNN plot. So we're going to call our function that we just created train, test, and I. So I is going to be, it's in the third spot in the function, so I don't have to say k is equal to I, although you could, and I think that would be okay. So it's going to say this is my training, this is my test, and the only thing changing is I. And then I'm going to use the command ggsave, file name is equal to filer I, so it takes the ith file name and plots it with a height and a width, and that's it. So let's go ahead and run this. First, let's save it. You don't want to save the whole R console ever. We just want to save the program. Okay, so it takes a minute to run. Okay. Okay, and what we can do is we can go, so it's finished running, it went through all 10. My computer fan's running kind of hard, so must have been tough work. And what we can do is we can go to the directory that we're in right now, and if you don't know where you are, you can always look here at this to see what directory you're going to find your stuff. And so if I look at Complabs here, I will find, here's the plot we plotted earlier, and here are the different plots. And you can see it's late here. It's 9:30. What we have is all of the plots are saved. So let's just go ahead. That kind of completes the coding part. But let's go ahead and look at the plots. Here's k is equal to 1. Okay, and so we see the boundaries. It's really neat. So this is the contour line piece. I don't know if there's any feasible way of doing this in R. I'm sorry, with the standard R graphics. But here we're able to do this really nicely. So k is equal to 1 says that each one of these test points is classified according to its closest training point. So we see how that works exactly. And we can see the boundaries. We have a lot of little boundaries. Now I'm going to go to k is equal to 9. K is equal to 9, if we can compare it to k is equal to 1, we see that it's quite different. Okay, and so here we have literally many more boundaries. Here we have far fewer, bigger regions. And so we'll see that as k gets bigger and bigger. That's just one of the things that we talked about with this particular method. And the other thing that we kind of talked about was that we always usually take even numbers. So let's actually look at k is equal to 5, and we can see that the regions are also kind of smoothing out. Now we have no idea from this how well each k is doing. What we would need to do if we were really using this method to analyze this data is we would actually look at the error. We don't really know what that error is. We would literally have to count all of the misclassifications. But in this case, since we didn't divide test and training, it doesn't really make sense in this context. We're simply looking for a visualization. So we have x1 and x2. We've generated this grid of test points, and we've colored them according to just to understand the regions. And these boundaries, these contour lines that we've plotted here, these are called decision boundaries, and we'll see them again and again in different methods. But this is kind of where the buck stops in terms of visualization. We can really do things only for two. in your homework, you're going to have to use k-nearest neighbors for a higher dimensional problem. You're going to be kind of going blind because you can't see what's going on, but you have other measures that you're going to have to use to track. The final thing I wanted to tell you about was the even number case. This is actually a common mistake. If you look at the even numbers, you see that they all kind of look crazy. The boundaries look crazy. The reason is that if a boundary if a test point is equidistant, so actually, if k is equal to 4, if two of the nearest neighbors are blue and two are red, what happens is literally it's randomly decided. So a coin is tossed and it decides to be blue, or a coin is tossed and decides to be red. That's why all of these points are totally, this decision could have gone either way, and so the boundary might look a little bit different. So this is a problem with the even numbers. We'd never use even numbers for that region because it would be an unreliable estimation of the error. And I hope that's clear. I think it's pretty obvious by looking at the boundaries. That's exactly why they look so shaky. And this also looks kind of smooth here. Okay, so this was kind of a fun exercise. I hope that the coding is clear. I try to be as clear as possible in terms of my rationale, what I'm thinking about when I do different things, how I execute a for loop, and how I think about writing functions. I could have written this function if it was more detailed. I would have written it in a different R file and used a command called source and sourced it in that way. But it's pretty straightforward anyways. Okay, I think that's just about it. Thank you.